Okay, good morning. Today we're going to do 7.3. We're going to be solving a system of three equations today. Um, so far in the homework on 7.1 and 7.2, you've only been doing two equations, so today is the first day with three equations. The first thing I want to show you is what's called row echelon form. It has this kind of staircase look to it. That's kind of a defining feature where one equation has three variables, the next equation only has two, and the third equation only has one variable. And if it's in this form, you use what's called back substitution. So what that means is we start with this last equation because it only has one variable and it's already solved for us, which is nice. They won't always be. It might be something like the last equation, as a side note, the last equation could be like 10z equals 50. Well, that'd be easy. You could solve for z and get 5. This is already solved for you. So um, what we're going to do is now that we know what z is, now we're going to substitute that back into that equation. So you'd have negative y plus 2 equals 4, because z is 2. We would subtract the 2, and then y would equal negative 2. And then we're going to substitute that and the negative 2 in for y and the 2 in for z and substitute those into the first equation. So we would have 4x minus 2 times y, which we found as negative 2, plus z, which we know is positive 2, equals 8. And now we're going to solve for x. So this would be a plus 4 plus 2. We get 4x plus 6 equals 8. We would subtract the 6 and then divide by 4 and reduce that down to 1/2. So x is 1/2, y is negative 2, and z is 2. But don't write your answer like that. Write it as a point, because what this represents is three planes intersecting at one point. It's a three-dimensional graph. And so the point would be x, y, z. So it would be 1/2, comma, negative 2, comma, 2. You have an x, a y, and a z plane. I'm not going to get into too many details, but here's how it would kind of look. You have your normal x and y, and then z comes out, like sticking out of the page at you. And I think what a lot of people tend to think of this as is like the corner of a room. Like, here's the floor, and then this is one wall, and then this is a other wall, and this would be like the corner of the room right here, and this would be like the floorboard and another floorboard, if you can kind of imagine that. So then this would be a point in three-dimensional space, which you don't need to worry about for right now. Okay, next page. Now you might be given an equation, that a set of equations that look like this, and it's not in that step form, where it looked like stairs leading down. I have three variables here, I have two variables there, but then I have three variables again. And I really want it, if I could, I would like it to look like that row echelon form. And we're going to get to that eventually when we use matrices. But for today, I just want to show you another way to solve systems of three equations. So The first thing I would say to do is pick two equations and eliminate one of the variables. Okay, so you could pick, I'll call this equation 1, 2, and 3. So I could pick either 1 and 2, 1 and 3, 2 and 3, and I want to eliminate one of the variables. So you just kind of look and you're going to go, what would be easy to get rid of? Well, I can see right away that with equation 1 and 2, I already have opposites. So I could eliminate these x's very easily. So if I take my equation 1 and my equation 2, I've got x minus 2y plus 3z equals 9, and I've got negative x plus 3y equals negative 4. And if I add them up, and again, you can only add when you have opposites, and I already have opposites, but when I add them up, the x's go away. I have 1y, 3z plus 0, I'd have 3z, and then 9 plus negative 4, I'd get a 5. Okay, well, as of right now, I can't do anything with that because I still have two variables. So what I want to do next is pick two different equations and eliminate the same variable. So I already chose 1 and 2. So now I need to either do 1 and 3 or 2 and 3. And I'm going to eliminate the x variable again. So I think I'm going to pick 2 and 3. And I'm going to multiply the second equation by 2. So let's see here. How do I want to write this out nicely? Okay, so I'm going to multiply this whole equation by 2. Okay, I'm trying to make it look nice. So the top equation is now going to be a negative 2x plus 6y equals negative 8. The bottom equation I'm going to leave. Okay, and that'll be a 17. Now I can add them up and eliminate the x's. So those will be gone. 6y minus 5y, I'll have a y. I'll have 5z still. And then negative 8 plus 17, we get a 9. Okay, so here's the thing. Look at this equation. It involves y's and z's. And look at this equation. It involves y's and z's. So if I put the two of those together, I want to solve those two. Now it goes back to what we did in section 7.1 and 7.2. I have two variables now. Maybe I'm going to draw some lines showing that we put those two equations together. Okay, so now if I'm going to solve those, I need to eliminate one of the variables. So I think I'll multiply this top equation by negative 1. So now I'll have a negative y minus 3z equals negative 5. The bottom equation I'll leave alone. So now I have my y's are opposites. So I'm going to add them up. The y's go away. Negative 3z plus 5z, I'll get a 2z. And then negative 5 plus 9, we'll get a 4. Divide that out by 2, you get z equals 2. So that's our z value. Okay, now we need to figure out where to plug that into. Well, I'm not going to plug it up into my original top equation here, because if I plug in something for z, I still don't know what y and x are, so that's not going to do me any good. So I want to plug it into one of these squiggled equations, because if I know z, I can find y. Or down here, if I plug in for z, I can find y. So that's what I'm going to do. So y plus 5 times 2 will equal 9. And then I'm going to subtract the 10, and I get negative 1. Okay, now that I know z and I know y, I can plug it up into any of the originals and get x. So I will choose, just for ease, I think I'll choose the second equation here. So negative x plus 3y equals negative 4. I'm solving for x. I know that y is negative 1. So then I get negative x minus 3 equals negative 4. I'm going to add the 3 over. So negative x will equal negative 1. So that means that x equals 1. And again, we write our answer as a coordinate point, x, y, z. So x is 1, y is negative 1, and z is 2. So that will be our answer. So just as a little recap, we picked two equations and eliminated one of the variables. I just happened to pick equation 1 and equation 2, and because the x's were already opposites. So that was easy to eliminate the x variable. I pick two different equations and eliminate the same variable. I'm still going to eliminate the x's. So I thought, well, if I use equation 2 and 3, it'd be pretty easy to eliminate these x's if I multiply this middle equation by 2. So that's what I did here. I showed that I was multiplying that equation by 2. So here's what I got. I kept the bottom equation the same. My x's are opposites, so when I add them up, they eliminate. So the x's are gone. So I take the y and z equations that I have and put those together. And now I only have two variables, and I can solve just like we did the last few days. So I chose to eliminate the y's. I multiplied this equation by negative 1. And then add them up. The y's went away and was able to find z. And then I plugged z back into one of these two equations and got y, and then plugged those into one of the original equations to get x. Okay, I have two more examples I want to do, so I'm going to record another video. So click the next video, okay?